Everyone, this is Suchita Sharma. My student ID is 10508514. My topic is Internet Protocol. So let me tell you about this, that it is an identifying number for network hardware connected to a network. Having an IP address allows a device to communicate with other devices over an IP-based network like an internet. So let's investigate the IP protocol focusing on the IP diagram. Let's do so by analyzing a trace of IP datagrams sent and received by an execution of the trace code program. Linkplotter is a nice Windows trace route program. So here let's take a trace first. I'll try www.facebook.com and set the focus to 3 seconds in the first round. Let's set the packet size to 56 bytes. Yes, and trace. Then let's change the packet size. Okay, now let's change the packet size to 2000. And trace back again. So it's getting traced. And ultimately, let's change the packet size to 3500. And see what it gives. Let's go to the Wireshark result and check now. According to the results, you can see that the IP address of my computer is 192.168.1.102. Within the IP packet header, the value in the upper layer protocol field is ICMP1. So it's here. And according to this record, the header length is 20 bytes and the total length is 84 bytes. Therefore, the payload of the datagram should be 60 bytes, that is 84 minus 20. Next, the IP fragmentation also occurs when an IP datagram transfers a network which has a maximum transmission until that the smaller the size of the datagram. According to this IP datagram, it is very clear that the IP datagram has not been fragmented, as we can see that most of the fragments bit are 0 here, and we will see that these later will transmit longer ICMP echo request. So let's check now that what fields always change from one datagram to the next within this series of ICMP messages sent by my computer. We can observe here that the change in identification, time to live, and the header checksum in the IP datagram always change. Identification changes because the IP packets have different IDs. Time to live changes because the trace route increments each packet, and header checksum changes because the header changes. So here the fields that remain constant are header length. That is because that does not change since we are always using IP version 4. And the source IP remains constant because my computer's IP address does not change. The destination IP also remains constant because of the domain IP address, which does not change, as well as differentiated services because of the same protocol every time, and upper layer protocol because of the same protocol every time, as well as the header checksum where the validation is disabled in my test, as you can see here. So you can see a pattern in the identification field in the IP datagram. In the first request, it has a value of 13008, and in the second request, it has a value of 13009. It is here. Yeah, so they are incrementing with each other datagram, as you can see here. time to live, that is TTL, it is a value in an IP packet that tells a network router whether or not that the packet has been in the network too long and should be discarded. So in this datagram, the identification field has a value of 40316, which I am showing here, and the TTL, that is 255. The values of identification field changes for all the ICMP TTL exceeded replies, since the identification field is a unique value. If two or more IP datagrams have the same identification value, then it means that these IP datagrams are fragments of a single large IP datagram. When I change the packet size in ping plotter to be 2000, before, like I have shown you, the messages have been fragmented across more than one IP datagram. We can confirm it by looking at the identification number and into the field. Now let's see the first fragment of the fragmented IP datagram. The information in the IP header indicates that the datagram has been fragmented. The flags bit for more fragments is set to 1, which means the datagram has been fragmented. The fragment offset is 0 here. So we know that this is the first fragment. The length of this fragment is the first fragment, that is 1500, including the header. Now let's see the second one. Okay, the second fragment of the fragmented IP datagram. Let's see what information in the IP header indicates that this is not the first datagram fragment. So according to this datagram, this is not the first fragment. Since the fragment offset is 185 here, and this should be the last fragment. Since the status of more fragments flag is not set, so now it is noticeable to us that the total length, flags, and fragment offset, as well as the checksum, change in the IP header between the first and the second fragment in this. And then at the last, it is the fragment offset and the checksum fields that change in the IP header among the fragments. Thank you.